Hey guys, welcome back to another Leetcode problem solving tutorial, and in this tutorial I'm going to be showing you guys how to solve Leetcode problem 208, which is asking us to implement a data structure called a trie, or a prefix tree. So a prefix tree is basically just a special type of tree which starts at a root node and it can contain only letters underneath it, or not just letters, but essentially the tree can spell out different prefixes and it can store words using a special format which allows it to easily search for words starting with their prefix. So I know that was a bit confusing, but let's look at an example. So in this example we want to insert apple into the trie. Well, what that basically is we store each letter as a prefix, or we store each letter as its own node nesting below individual other nodes. So apple would be stored like this. I know that's a bit small, but yeah, so this is how apple would be stored. Starting from the root node, we know the first letter is A, then second letter is P, and we just go along and spell the whole of apple like so. And you can see if we were searching for a prefix, like if we were searching for words starting with APP, well, all we'd have to do is go along to APP and then look at all the different roots from here, and that's all the words which this tree contains starting with APP. So the idea of this is that we can store multiple words by grouping them together by prefix and then separating them when necessary. For example, if we had something like, okay, so we have apple already, but let's say we wanted to just add apps. So apps as in, like, I don't know, applications, something like that. If we wanted to add that in, well, you can see we've already got the APP inside the tree, so instead of going L next, we can just add an S, and that's essentially added the word apps into our tree. So now we have apple and apps. And one thing you might notice is, how do we tell when a word has ended? Like, because how do we know we haven't just added APP? Or how do we check that we haven't added APP? Because right now there's no way of telling. Like, for example, if we added both the word apple and apples, well, adding the word apples would be equivalent to adding an S at the end of this. But now how do we tell that the word apple on its own is in here without apples? Because it seems a bit confusing. Well, that's why one thing we can do is add an end character, and this can be anything. You just need to make sure it can't be used by any words. So I'm going to use a hashtag, and essentially what I can do now is just add a final node onto the end of each word, which essentially marks that if we can go apple and then over here to another node, then we're searching for just apple. So when we search for words, we want to search for the words with the hashtag at the end. This just ensures there's always an end character at the end, and then we can just search for them like this, and we can be sure that the actual word exists and it's not just a substring of another word. For example, if apples didn't exist, then this hashtag wouldn't be here. So then when we search for apple like this, we'd get here and notice that there's nothing there, so we could conclude that apple doesn't exist. That's the basic idea of a trie, just a big tree. And yeah, it's called a prefix tree because, as you can see, it's sorted by prefix. If we want to find all the words beginning with A, we just have to go into this node and then select all the words in here, nice and simply. But yeah, now let's see if we can implement this data structure into our programs, so into TypeScript or JavaScript. Now what I'm going to use to sort of try is actually going to be, well, I'm just going to use a hash map, and the reason for that is so we can get constant access time. So if we call the dummy node to be this, or the root node is this, then our hash map is going to be, well, we'd have A and then its corresponding hash map, and since there's no other letters, we're not going to have any other letters. But now if we go into here, so this is the hash map for A, this is going to have a P, its corresponding hash map, and nothing else. And then if we go into this hash map, this is now currently here, this is going to have another P, and this hash map, since we're here, these basically represent the next possible route. So it's going to have an L, its corresponding hash map, or we can have an S with its corresponding hash map, like so. And yeah, that's basically demonstrating the next possible routes from this P onto next letters. And this is just going to be all nested inside of each other. And basically we're going to traverse it like a tree, but we're just storing it in hash maps, nice and simply. So yeah, let's just implement this now. So class try, let's create a entry, and this is just going to be this node here. I'll just define this to be a hash map, so it's going to have a key of string, and it's going to map to another hash map. I'll just put any, since we don't really need to be worrying about all of that, but yeah, it's going to be of entry any. And when we initialize this, we can just do this.entry is empty, like so. Okay, so if we insert a word, we're going to start at the root node, and for each letter in the word, we're just going to check whether the root already exists. If it does, then we'll go into it, but if it doesn't exist, so let's say we wanted to add bus into this, well, there's no B here, so we need to add a B to the hash map, to the list of next possible letters, and then we just go from there, and then we just continue like that. So essentially what this entry hash map represents is the next possible letters, like that. So starting from here, and it represents the next possible letters we can take, or the next possible paths. And I'm just going to loop through the letters for constant letter of word. Just going to loop through this, and we want to check if letter is a next possible path from the current node, so from here. And to do that, we can just do something like if next possible letters is not defined. Well, if it is not undefined, that means it exists, and we want to handle the case if it is undefined. So if we're in here, it must mean this path doesn't exist yet. So let's create it. And to create a path, pretty simple. We just have to start a new hash map from within it. So if we add in B, this is equivalent to just creating this B and then just creating an empty hash map to represent the next possible letters from there. Okay, and once we've done that, now from here we know this letter must exist in the next possible paths, and we can just increment this next possible letters by doing this. So similar to if you were in a linked list, or a tree, you'll just go into the next index at that position and then incrementing your current pointer like that. So there we go, nice and simple. And one last thing, we need to add our end character, which I said was going to be a hash map. Alright, there we go. So here's how we insert a word. You can see if we use Apple, it's just going to keep on going through, and well, if we imagine this hash map was empty, it's just going to keep adding these in like so, and once it gets here, it's going to add this hash, and then we're going to end up on this final root like so. Sorry, I shouldn't have scribbled out this hash, but you get the idea. Okay, so nothing to do there, we've completely finished that. Now, well, I'll search for this word, but I think it would be a better idea if we implement this starts with function first. Because once we implement the starts with function, we can simply just add this end character to the word and use the starts with function. So what we want to do is same sort of thing. We're just going to do let next possible letters equals this.entry, starting from the entry point again. And we want to check if there's a word starting with this prefix. So if we was, for example, searching for app or app, well, we just want to check if A exists, then if P exists, and then if another P exists from there. So for const letter of prefix, check if letter is a possible path. If not, then prefix doesn't exist in the trie, so return false. Like that. So we want to check for each letter if it exists as the next possible path. If it doesn't, we're going to return false. So we do if next possible letter is undefined, then this path doesn't exist. Like, let's say we were searching for APB, we'd get to A, we get to P, but then we check for B and it doesn't exist. So we return false because this prefix doesn't exist. And then we're just going to increment next possible letters to go to the next step, like that. Alright, there we go. If you don't understand this line, it's essentially, so if we start here, we check for A, it exists, so we get past this, but then the next possible letters is currently on this hash map here, and we just want to, it's this hash map, and we want to go here, so we now want to be inside of this hash map, like so. So we just set this to be equal to that, and that basically increments it. Nice and simply, if we get through the entire word and all the letters are there, then that must mean the prefix exists, so we return true, like that. And now all we have to do is this, we've implemented this starts with a prefix. So now if we want to search for a specific word, well, that means we're searching for the whole word, and we need to check whether it exists with the hashtag in it, because this marks the end character. So we can just return this dot starts with and word plus hashtag search for entire word with end character, like so. Because if we were just searching for the word, then if we were searching for apple and we hadn't actually added apple but we'd added apples, then starts with would return true since the apple prefix exists. But if we add this end character, now it's going to look for apple and then this end character, which is going to check if a whole word exists. So there we go, that's how we implement a trie in JavaScript. Did this all using hash maps, so no classes, although if you were to implement it, you would likely want to use classes just so it's a bit cleaner. But yeah, this was the trie implementation. Let's submit this and see what we get. Alright, there we go. So yeah, like I said, I'm pretty sure this hash map implementation is actually a lot faster compared with a class implementation, just because hash maps are usually optimized, as well as the fact that we're using this end character rather than using specific attributes on a class. But yeah, that was pretty good, getting to the 90th percentile. So that was how we solve Leetcode question 208, asking us to implement a prefix tree. See you guys in a future tutorial. Bye.